because it's not my computer.
Yes, now
it's better to be on the cloud. Okay, so today we continue discussing the derivation of hydrodynamic equation from kinetics in this hybrid fashion. It's very interesting. Never had this experience before. So let me just remind you the logic. So we want to reach the states of hydrodynamic theory starting from Boltzmann equation. So we are given our favorite. So this was okay. Okay.
Is it possible to enlarge your window a bit?
Better?
No, maybe in the computer, maybe
you can just turn it around and make full screen. No. Just okay, let's. Who is good at so I just suggest you do just this and
yeah, this looks better.
Shake it.
Now you can place the arrow on the side and
yeah, I'm trying.
I think
like this and more. Yeah.
Maybe it needs to be extra accurate.
Okay, but this is better, right?
Yeah, anyway, this is better. Now we just need to move the zoom window to the left, maybe, so it won't be over when. No, like the black square.
Maybe just.
Yeah.
You don't need to.
I see.
Okay, so how about now? D over dt, right, times F plus V P grad RF plus force grad F is equal to collision integral. And starting from this equation, we want to, that's our starting point. And let's say we have electrons interacting with electron-electron interaction. And we want to derive less microscopic equation, more macroscopic equation, which is hydrodynamic of electrons. So the logic is that we're going from something microscopic towards something macroscopic. And something microscopic, it's Boltzmann equation, and macroscopic is a classical hydrodynamics. Okay, so as we said last time, there are conservation laws that are satisfied by classical collision, conservation law of electron-electron collisions. And these are particle number, a total momentum, and total energy of electronic system. And technically, or more formally, it means that the integral over pi collision integral of the distribution function is equal to 0 and also equal to 0. Okay, so now let us see how we can get equations of hydrodynamics. And now let's, for simplicity.
And when did you say this is 0? I was busy copying. So.
Because it's the total energy, and total energy is not changed in the process of electron-electron scattering. So if you have several electrons scattering, each and every electron changes its energy, but the total energy of electrons as a whole does not change. Okay, let's say for simplicity, that there are no external fields. Just make the life easier. Then the equation reads and we can switch fields later on if we want. Okay, so the first equation to derive is a continuity equation that tells that the particle number is conserved. How we derive continuity equation from here? Well, actually, it's a very simple way to derive continuity equation. The only thing one needs to do is to realize that the density, particle density at the point r at the time t is an integral over dp of f of p r and t. So one takes the density in the phase space and sums over all the momentum, one gets the density in the real space. So if I take the Boltzmann equation and integrate the Boltzmann equation with respect to momentum, this is what the Boltzmann equation, I'm supposed to get the continuity equation. Okay, so how does it work? I'm taking my equation and I'm integrating dp. That's the first term plus vp gradient r of p minus collision integral. All this is equal to 0. Then the first term, I can obviously switch the order of integration and differentiation. Therefore, I'm getting d over dt integral over d dp of f of p r and t. Then there's a second term. And the second term, it's a gradient of an integral vp f. And there's a last term, which is an integration of collision integral with respect to momentum, but as we mentioned 5 minutes ago, integral over collision integral f of p is equal to 0, and therefore this term drops. And we get 0. Okay, then, as we said, this thing in the first integral is just by definition, is a particle density at the point r time t. So we are getting d over dt of a particle density plus divergence of the something that we'll call vector j is equal to 0, where vector j is an object that we just defined, and it's so this is the familiar object that you know. This is what we used in Boltzmann equation when we computed, say, electric current or particle current. And lo and behold, we got precisely this. Sometimes one can divide another object. So this is, so let me just call it, this was, to give a proper name, this was a particle particle current. We can define velocity field. Velocity of the fluid, which was never defined before. So this is not to be confused with the velocity of particles with sub p. So I define it using the following relation. I'm writing current operator as a function r and t is equal to density as a function r and t times velocity as a function r and t. This is for me a definition of velocity. I could have written this in this. That's a definition of the velocity. And then the continuity equation reads so this is the first of the fundamental hydrodynamic equations. Altogether, we need to have 3 equations that corresponds to the particle momentum and energy conservation. We got the first one, very relatively easy. Okay, so now we will try to derive Navier-Stokes. So this is something that's called continuity equation in the hydrodynamic textbooks. Are we good? Okay. Then let's go and describe next equation. So next goal is to compute, to derive Navier-Stokes equation. Navier-Stokes equation. Okay, so how are we gonna derive that? So we start again from the same Boltzmann equation as we always do, and we multiply this time. We multiply Boltzmann equation by m times v. So by the way, Navier-Stokes equation, for those of you who doesn't know, so this is an equation for velocity, so it's a vector equation. Yeah? So one writes equation for velocity. Velocity is a vector, and being, say, 3-dimensional space, it means that these are actually 3 scalar equations. So let us look at some component of this equation. Let's multiply by mv alpha. Alpha is one of the labels x, y, or z, depending on what component we choose to study. Okay. Sorry, I said something terribly wrong. Just a sec. No, I said something. I'm sorry, I said something terribly wrong. Forget it. I assume that my spectrum, I wanted to say something, let us different. I wanted to say, let us multiply by m v alpha. V alpha is by definition d epsilon p over dp alpha. Sorry, I got confused by my own notation. So we're going to multiply Boltzmann equation by quasi-particle velocity, not by hydrodynamic velocity. I was too fast.
So it's just velocity in phase space.
That's a velocity of a quasi-particle in phase space. So for parabolic spectrum, for EP being equal to p squared over 2m, P1, P alpha will, sorry, V alpha will be just P alpha over M. Okay, sorry. Then what happens with Boltzmann equation? So let's look at this schematically. And okay, let's stay with this spectrum to make things easier. I'm cheating a little bit because what I'm saying can be done for a more general spectrum, but will be talking about parabolic spectrum because it's easier for me. And it's definitely a good starting point. Okay, so what happens when we multiply? So we have Boltzmann equation. Let me write it d over dt f plus v p grad f is equal to collision integral acting on f of p. And now I multiply each and every term by mv alpha. So mv alpha for this spectrum is just p alpha. So I multiply it by p alpha, and p alpha. And now I'm integrating Boltzmann equation with respect to dp. And notice that because of the property that we discussed above, the collision integral drops. Because I multiply collision integral by the momentum, and the total momentum is conserved, therefore the integral of this integral drops. And therefore I'm having an equation d over dt integral over dp p alpha f of p r and t plus plus integral over d3p p alpha v beta d beta f with all component that's equal to 0. And I can take this guy out. I can take this guy now out and write it d over d r beta. So yeah. Now the first term on the left, it's something that we already know.
Can you explain again how did you get from the upper row to the lower row?
Well, there are 3 terms. Term number 1, term number 2, and term number 3. So which one?
The right thing I got.
Okay. The term on the first term.
Okay.
Did you get that one?
No, I want to go over the left side of the equation. Like
this term?
Yes.
Do you understand it?
No.
Okay. So let's discuss this term. So we have an equation d3p p alpha d over dt f of p r and t.
Okay.
Then I'm gonna say this is a partial derivative with respect to time. I can take it out of the integral.
Oh, that's all you did in the left term?
Yes.
Okay, but in the right term, there's more to it.
Wait. So the first term, so this is the first term. Okay.
So you're just saying P doesn't depend on time?
P does not depend on time because P is a variable of integration. It's the momentum of a particle I'm integrating over momentum of the particle. Therefore, I'm allowed to exchange this thing with the derivative. Okay. Now second term is d3p Now let us write it carefully. What was the second term? It was
P alpha
P alpha, and the dot product of P dot gradient F of P R and T. Okay, so now let me write this dot product, this 3P, this is P alpha, V, say beta, grad beta, sum with respect to beta, yeah?
Oh, you just did it, okay.
F, P, R, and T. But now I can take and say for each and every component, I'm now taking this. So sum of beta, grad beta, integral D3, P alpha, B beta. Don't pay attention to low and upper indexes. I'm not meaning much right now about this. So just wanna. That's it, and therefore this is exactly the second term.
Yes, it's okay. Just
okay.
Missed it. Okay.
So now we have all the terms together. Now, so coming back, let us look and examine closely the first term. We have seen it before. We've seen this term before. And this term, we saw it before, we gave it a name.
Momentum density?
It has two names actually. It has a name of momentum density, and it also has a name of a particle current. Both statements are correct. For parabolic spectrum, the momentum density and particle current are the same. Okay, so this is precisely particle current, and we also call it rho times V capital. This meaning V capital being a hydrodynamic velocity, not to be confused with particle velocity. That I was confused myself a minute ago. Okay, so the first term is already something simple. So we see that the equation has a structure d over dt of rho times V alpha. We are looking at alpha component of this equation, plus gradient with respect to our beta component. And here will be an integral over d3p, V alpha sub p, V beta sub p, F of p, R and T, and was a factor of mass. And all this is equal to 0. All this is equal to 0. Now, what is nice about this object, that I'm getting a time derivative of something plus divergence of some tensor. So I can look at all these things and say that this is actually a tensor that has two components, alpha and beta, and it depends on R and T. So schematically, I'm getting an equation that looks d over dt rho times V alpha, all functions of R and T, plus V alpha beta R and T is equal to 0. And this tensor has a name in hydrodynamics, and it's called momentum flux. So what does it mean, momentum flux? So normally flux is when something flows. So flux of density is what we normally call a momentum. And this is flux of the momentum. So how much momentum in the direction alpha flows in the direction beta. Momentum is a vector, so you look at the component of the momentum in alpha direction and ask how much of this flows in the direction beta. That's something to think about. But that's its formal definition. We will talk a bit more about this later. Now let me just get the last equation of hydrodynamic type. Yeah, and equation of this type, they always call hydrodynamic equations because they always written as conservation equation. Something is conserved. It's very similar to the continuity equation. You compare rho plus is equal to 0, something plus divergence of a current. A derivative with respect of time of a charge plus divergence of a current is equal to 0. Now the charge itself becomes a vector, and instead of a current, we now get a tensor. Okay, so now how about energy conservation? So let's multiply Boltzmann equation.
You got to the current. How did you get from here to here? How did you get rid of the V alpha and the?
I didn't get rid of anything.
It's just the previous equation, or you got from?
No, so there are two equations now. So this is continuity equation.
So you just
I'm just comparing
again the equation from before.
Yes.
Okay.
I'm just showing you that this equation has a similar form.
Okay.
And this equation, which is Navier-Stokes equation, it's written very schematically because I haven't said you anything about the properties of this tensor. I just wrote that this object. I see that I'm getting something which is a full derivative, and it's built of distribution function and integrated with these components, V alpha and V beta, and I don't know anything intelligent to say about this object right now. I will say something intelligent later on. Finally, by the same procedure, I multiply Boltzmann equation by quasi-particle energy. Then the same story over and over again, the term with collision integral will drop because the total energy is conserved, and I also allow to interchange the order of derivatives and integrals. So then my equation reads epsilon p f p r and t plus gradient of r integral over d3p epsilon of p v of p f p r and t equals 0, and indices should be, yeah, I'm signing over bit. And once again,
equals to 0.
Equal to 0. The first term is just the density of energy. And the second term, it's again a derivative of a flux, and this time, let me call it Q of R and T. This will be definition. And this is energy flux. So the equation for energy distribution looks, this is energy. Looks as continuity equation again. Now, these three equations should hold regardless of how accurately we have computed the collision integral. They follow solely from conservation law. So it does not matter to what accuracy we compute collision integral. To any orders in perturbation theory, this equation should hold. However, what is lacking right now at this point, that we need to relate these quantities observable hydrodynamical variables. Yeah? We just given them name, but it's not very helpful. We need to connect them and write this object in terms of density and velocity of the fluid. Then we'll be in business of solving hydrodynamic equations. Okay, so we need to establish, we need to connect these guys to hydrodynamic velocity, density, and temperature. See, things that can be measured in the experiment. Okay, so how do we do it? Once again, we go back to our favorite Boltzmann equation and say, look, the only reason why hydrodynamic works, it's because we were looking at the system at the scales which are much, much greater than an elastic length. Otherwise, there is absolutely no reason why the system can be approximated by hydrodynamic equations. So, what can we say about the system if we know that its length is much greater than the collision integral? Sorry, that the inelastic length. It means that collision integral is the most dominant part of the Boltzmann equation. And it means that when we attempt to solve Boltzmann equation, we must first of all nullify the collision integral. So solution of the Boltzmann equation in this case will be roughly an equilibrium solution plus small correction. And as we discussed, the equilibrium solution still allows for 3 low energy modes: boost velocity, chemical potential, and temperature. Okay? So we can now treat these guys as slowly varying classical fields. And on this solution, the collision integral acting on F Fermi-Dirac will yield 0. Now, so what we can do, we can say, okay, let us in the leading order, let us only look at this part of the Boltzmann equation. Let us assume that distribution function is effectively locally equilibrium distribution function and ignore small corrections. Then we parameterize this solution by 3 classical fields: boost velocity, chemical potential, and temperature. And let us now substitute these ansatz into equations we derived above, say for the momentum flux, and see what and density and so on, and see what it gives. And now we will have an explicit equation written in these terms. So let us see what it says. Let's go back to density. Density, as we say, is d3p f of p r and t. Now we plug this simplified solution, epsilon p minus v times p minus nu divided by t plus 1. assuming that chemical potential, temperature, and V are all time and coordinate dependent. And now, okay, let us compute this integral. Assume that temperature is much smaller than epsilon Fermi. Therefore, I can employ Bohr-Sommerfeld expansion. And this integral will be integral over d3 p from 0 to p Fermi plus small corrections. And essentially this integral is 1 over 2 pi cube, 4 pi over 3 p Fermi cube plus T over epsilon Fermi. So we now have a relation between and mind you, I also know that P Fermi square over 2m is chemical potential. Therefore, I can conclude, just like I'm trying to see what is there. What I want to say? Right now, no, probably I'm good. Probably I want to say that in the low temperature limit, so if I just ignore this term, as a first approximation, that's what I'm finding, that rho as a function of R and T is m over 6 pi square p Fermi cube. Okay. Now, let me look at the current component in the direction alpha. This will be the integral d3 v alpha f of p. I'm plugging this spectrum, p alpha divided epsilon p minus v times p minus nu over t plus 1. Okay. This is equal to 1 over m d3 p alpha plus m v alpha times e in the power epsilon p minus m v square over 2 minus nu divided by temperature plus 1. And I'm using the symmetry arguments to claim that the first part of this integral drops because it's an odd function of the momentum. And I end up having m v alpha divided by m integral d3 pi function Fermi-Dirac epsilon p minus nu minus mv square over 2. And this is approximately equal to v alpha times rho at R and T. Okay, so now I'm playing the same game with momentum flux, so P alpha beta. It's M integral D3P V alpha V beta times F Fermi Dirac at epsilon P minus V P minus nu divided by temperature. And this is 1 over M integral D3P P alpha P beta F Fermi Dirac epsilon P minus V times P minus nu divided by temperature. Now I'm doing the shift again. And I'm getting D3P P alpha plus V alpha P beta, sorry, plus MV alpha. Plus M V beta plus MV beta F of epsilon P minus nu divided by temperature. I'm ignoring terms that are of the order of V squared in the distribution function. And I am getting object 1 over M D3P P alpha P beta F, this is beta, epsilon P minus nu over temperature plus V alpha V beta times rho. And
so may I ask something? So why did you ignore V squared terms in the distribution function?
Okay, let's restore them and see why they drop, okay? So I'm shifting this. So it would mean here will be terms like V squared over 2M, yeah? Okay, so let's add them there and see how they disappear.
Maybe just symmetric.
Okay, so now we have two terms. So there are terms that are already proportional to V squared times rho. So you are right that this is not the same rho at the beginning. So this rho is a function of, okay, let me write, let me slow emoke. So we have here two types of terms. So we now have terms that are 1 over M integral D3 pi P alpha P beta F of epsilon P minus nu plus V squared over 2M divided by temperature plus term which is plus V alpha V beta integral D3P F of epsilon P plus V squared over 2M minus nu divided by temperature. Okay, so everything is kosher. Okay. So the second term, now we are assuming that these are hydrodynamic fields. So it means that they are, this thing is much, much smaller than chemical potential.
Why is it much smaller?
By
Why v square over 2m is much smaller than the...
For simplicity.
You just assume that?
No, I assumed that long time ago. Maybe I didn't write. I think I did. Let's assume this for simplicity.
There is a physical...
Well, because normally chemical potential is electron volts.
It's like Fermi energy, right?
So it means that for these to become, so it means like, so essentially you compare V hydrodynamic velocity with Fermi velocity. Fermi velocity is typical 10 to the power 6 meters per second. So unless you are willing to study fluid that flow at almost relativistic speed, you can safely ignore these terms.
Okay.
Okay, just let's do the simplest limit first, because it's already sufficiently interesting and complicated. So it means that we generated something which is already second order in hydrodynamic velocities. So of course we can now take this function and Sommerfeld expand it in hydrodynamic velocity further, and this will generate terms that are v in the power 4. So there will be expansion that starts with the hydrodynamic velocity square, but will also now generate terms that are high and more nonlinear. Now let's use the approximation that v is much smaller than Fermi velocity, and therefore just ignore these terms there. Okay. So it means that this term here yields something very familiar for people who study hydrodynamics. This is density times V alpha RT times V beta of RT. And then there is this piece. There is this piece of the tensor. That's the first. Let me use a different color. There's the first element. And I will call it P of rho. And I claim that this thing is nothing but a pressure. So first of all, you can see that this thing vanishes if alpha is not equal to beta for symmetry reason. If alpha is not equal to beta, this thing simply vanishes. Okay, so I'm now taking this thing and also Sommerfeld expanding it. So you are right, Paulina, I would have an infinite series of terms. The first term will start with the velocity in the power 0, and then I'll generate infinitely many terms that will be velocity in the power 2n. So the first term will be delta Kronecker delta function alpha beta divided by m square divided by 2 pi cube. So I'm just omitting here. This thing and computing integral p alpha square with a Fermi-Dirac distribution function. You seem to be not happy. Okay, so let me do it slower. So let me now look at the first term. So this term, green term. So this term, and I claim that I call it P, and I claim it's going to be pressure. So what is it? It's 1 over m integral d3p p alpha p beta f of epsilon p minus nu divided by temperature. Now, okay, I'm saying that this is delta alpha beta over m integral d3p p alpha square f of epsilon p minus nu divided by temperature.
Okay.
Now, okay, so now let's look at the low temperature limit. So let's assume that temperature is also much smaller than chemical potential. Then what is this integral? This integral is, okay, it's an integral p squared dp over 2 pi integral sine theta d theta over 2 pi integral d phi over 2 pi p.
You just changed coordinate?
I'm just suggesting let's compute this integral in spherical. Let's choose alpha to be I don't know, x or z. Let's just, yeah, and then will be p. What is that? Cosine theta square p square, and the distribution function epsilon p minus nu over temperature. Right? Now, this thing does not depend on angles. So distribution function is something that changes between 1 and 0 at P Fermi. So it means I can cut it here and write its integral from 0 to P Fermi. And then I just have a polynomial integrals that we can easily perform. And then we get that this is equal to delta alpha beta over 10 pi square m square P Fermi in the power of 5. And we see it's 5, 2, 4, 5. But we also remember there was a simple relation between density and P Fermi, and that was m over 6 pi square P Fermi cube. Therefore, we can rewrite the pressure and say that the pressure is equal to delta alpha beta divided by 10 pi square m square 6 pi rho in the power 5/3. And this is unique formula that says what is the pressure as a function of density for three-dimensional degenerate electron gas. So what we used here that these are electrons with a spectrum epsilon k equal k square over 2m. We use that d equal 3, and we use that the gas was degenerate. So these things that were used here, once they were used, they got a relation between pressure as a function of coordinate and time through density as a function of coordinate and time. So if you know locally what is the density of electrons, you know what would be the pressure at the same point. Now we born Sommerfeld many times. So it means that to this formula will be corrections that will be proportional to temperature of epsilon Fermi in different powers that we missed. So if you want to go, so this expression is exact at t equals 0 limit, and it may require some additions at fine temperatures. I didn't have a question.
Yes. So I got lost a little bit. So why it's pressure? Why this thing has a
meaning of pressure? So, okay, so that's nothing to do with computation. So we got P alpha beta, so let me just write it down, is equal to delta alpha beta times pressure plus rho V alpha V beta. And the meaning of this P alpha beta, this object was defined as d over dt rho V alpha plus d beta, dr component beta of P alpha beta is equal to 0. So this was essentially momentum. This was this, well, you call it momentum conservation of the second law of Newton. Now, why don't you like here? What don't you like it? Okay. I don't know.
Yeah, okay, it's fine.
No, it's if you just look at the textbook and hydrodynamics, you will see that this tensor has this structure. So the term with delta alpha beta, it's by construction pressure. So imagine that the fluid would not flow, so this V capital will be 0. Then what this equation will tell you that so this guy is a current. So it will tell you that the time derivative of the current is the gradient of a pressure. So you apply
like force.
Yes. Okay. So we're writing. So let me try to say. So we're writing something which is a momentum. Yeah. So we know that momentum over dt is equal to force. So that's what we're writing. So force here. Now, if you have pressure number 1 and pressure 2 here and there, then there will be a force which is this is a delta x. This is a P in the point x. This is the P at the point x plus delta x. So let's write the balance of forces. So there will be a balance of forces for the cross-section delta S. So with delta S times P x plus delta x, that will be acting on the left, plus P at x acting on the right. That's the force. So now let's expand it, and we will get a delta S equal minus dP dx times delta x. Okay. So that's exactly the force that acts on an element of fluid. So we got classical equations of fluid. We got Navier-Stokes equation, and if we work for another half an hour, we'll get equation for energy. However, these are almost equation, almost Navier-Stokes equation. Something is still missing. What is missing? Something very big and conceptual is missing from the Navier-Stokes equation. What do we have in the Navier-Stokes equation that we don't have in the equation that we just derived?
You mean in the equation that you just, yeah, with this P.
Yeah, but we can, if you don't like P, let's substitute it. So we'll get an equation. We have an equation that says d over dt rho times V plus gradient component beta delta alpha beta P. This was R alpha plus V alpha, sorry, plus rho V alpha V beta equals 0 and was a sum with respect to beta. So I claim that this is almost a Navier-Stokes equation, but not quite. Something is missing.
Okay, so we maybe viscosity.
Correct. That's exactly what is missing. So what we got right now, it's classical fluid with no viscosity. So there's absolutely no, in this equation, there is no viscosity. And what is viscosity? Viscosity is if you have a wall and there's a fluid that flows next to this wall, there's a friction between moving fluid and the standing wall, and the wall will slow down the fluid. So if you will have a wall and you'll draw a velocity profile as a function of coordinate, and you have a wall, then here the velocity will vanish. If you have a pipe, then the typical flow in the pipe looks like this. It's a maximum velocity far from the wall, and there is a 0 velocity at the wall.
I didn't get the last sentence. What do you mean? Can you repeat again what the...
So velocity, sorry. Viscosity is something that characterizes the friction between the fluid and the standing wall, or between fluid layers. So if you imagine you have a moving fluid layer and a standing fluid layer. So and then there's, due to the friction, there will be the standing fluid layer will start moving.
Okay.
So this is called viscosity. And viscosity is very important because if you drop the viscosity, then your classical fluid will be very similar to superconductor. So if you have no viscosity, imagine you have no viscosity, it's like having a car and no friction. So if you have a car and there is no friction in this world, you will never be able to stop. You will keep moving forever, right? So the only way to stop the car is by dissipating the energy of kinematic motion to the heat on the road. That's what happens. And for that, you need friction. So friction in fluids is called viscosity in the most simplest form. And if there's no friction, then these fluids will flow forever, like currents in superconductors. Now, where did we lose velocity and how can we, where did we lose viscosity and how can we fix it? Find the place where we lost the viscosity.
Well, in the beginning, like we assumed that there was a term in Boltzmann equation. It's force, right?
No, force, no. Force you can, force will not change anything. It will just take the computation longer. where it was hiding viscosity.
Well, maybe in energy conservation, no?
Exactly. More ideas.
What do you mean?
All the conservation. So momentum conservation, energy conservation.
No, energy conservation is exact. Momentum conservation is exact. And particle number is exact. Okay, I'll tell you where we made the mistake. We made the mistake here. And we said that distribution function is locally at equilibrium, and we're going to neglect the corrections. So it was, the statement was that, I mean, this statement was correct, and this term is indeed small, and it would be small because the term with viscosity is normally small. However, extremely important for friction. So that will be it will be small term, but that will be the only term that causes energy dissipation. So therefore, though this term is small and there is a small parameter coming with it, that will be the only term that will generate energy dissipation, and therefore
Energy what?
Energy dissipation. And therefore, one needs to keep this term into account if one wants to have viscous fluid and not viscosless fluid. Okay, so let's do it. Let's correct our computation. Let us try to think how we compute this term. So now,
but I have like, I think I don't understand so viscosity. So when a fluid flows and there is viscosity, so viscosity is kind of friction. So you exchange energy between fluid and walls.
Correct. Also inside the fluid. Between different layers that move at different velocities.
Yeah, maybe it heats up or something.
Yes, correct.
When it flows.
Yes.
And loses the velocity. But you say that energy conservation law that we wrote with this integral over epsilon p times collision integral 0. This means that kind of this is the energy conservation law, like right?
Oh, so I see what confused here. You say is energy conserved or energy is not conserved?
Energy of fluid or energy like fluid plus balls?
No, okay.
If you consider the fluid not connected to the wall, so it's exactly conserved. But if you consider the fluid is touching the wall, but the velocity is 0, so it doesn't matter.
Not sure. So the equation is whether just a second. It's equation. So we have a fluid that flows through the system, and now we're asking if the entire energy of the fluid is conserved in the presence of the viscosity. So we take the following. Let's do the following experiment. We take a glass of water, rotate the glass of water, so everything rotates, and then we place this glass of water on the table, right? So at the beginning, there is an energy of the rotating fluid in the glass of water, right? So if it would be no friction, this water would rotate forever, right? Which is in superconductivity, it's called persistent current. Now you're saying that you have a glass that it's actually placed on the table, and the last layer is actually here. So this is actually glass. All other green lines were flow of fluid, and this is a glass.
You address only the friction between the last layer and the glass, or the friction between each layer?
Friction is something that you just put in the fluid. So there's a characteristic of the fluid, which is called a friction. And it describes a friction in the fluid. It does not matter. It doesn't matter. And friction is something which is only sensitive to the gradient of the velocity. It doesn't matter how this gradient of velocity was created. Okay, just let's not go into the details with the current resolution. There is a parameter of the fluid which is called friction, and it prevents the fluid from having a gradient of velocity.
No, what I asked if what
and it exists everywhere in the fluid. Friction exists everywhere in the fluid.
Yes, but what stops the circling is mostly the touching between the last layer and the glass, or each layer between each layer?
I think the equation is ill-defined, all right? So we have a system, it's a complex system. And it starts in a well-defined state. Water in the glass rotates around it, and glass stands on the table, and there's a finite friction inside the fluid. And friction acts everywhere in the fluid. If there would be no friction, then this thing will rotate forever. Now there is a finite friction between the fluid and the glass. So what will eventually happen in this problem, that after sufficiently long time, the whole system will be just standing still. And you would ask where the kinetic energy went, yeah? Where did it go?
Has to become heat, but
it became heat, yes. It became heat. So what happened in this story is that if you thermally isolate your glass, let's make this glass to be thermally isolated, then what will happen that this this thing will heat itself. So the energy inside this glass will be conserved. However, it will go from the kinetic degrees of freedom to just thermal degrees of freedom. So if there is an energy conservation, of course there is an energy conservation in fact.
Yeah, like glass plus water.
Well, if the glass is thermally isolated, then just water. Mm-hmm. Imagine that you have ideally thermally isolated glass.
You mean like from the environment?
From the environment, yes. So that's a thin glass, completely thermally isolated. With zero thermal conductivity.
Okay.
So the thermal conductivity of glass is zero.
Okay.
Glass does not absorb any thermal energy.
Okay. Yeah. Okay.
So then all the energy inside the fluid is conserved. It's still the energy is still inside the fluid.
Okay.
But instead of being energy of global motion, it became the energy of chaotic molecular motion.
Okay. So like we can still write this. Like,
so
conservation law in this integral thing, right? Mm-hmm. If you assume that glass, like walls of glass, is like thermally isolated and doesn't heat up, essentially.
So no, you only say that So if there is no sink of energy from the system, but the same you assume when you say there is no sink of particles. Yeah, you're right. Particle conservation equation. Of course, you can say there is a sink somewhere in my pipe, and that's the place where my water molecules disappear. Eh? And then my particle conservation will be also violated. Yeah, there's a hole in my pipe, but if you don't assume that and you say that my system and it's thermally isolated, then the energy inside this system is conserved, and therefore my hydrodynamic equation makes a perfect sense.
In this case, if the system is thermally isolated, then the water or the air above the water inside this glass wouldn't expand from the heat. And then there will be some pressure involved.
Right. Strictly speaking, yes. But yes, so you need to specify your condition. You can have an isobaric glass such that you maintain it at a constant pressure. Or not. Look, it's all these are possible realization of this thought experiment, but the only thing that I was trying to say that it's due to this viscosity, the water in this experiment will stop or not. And therefore these terms should be taken seriously. Okay. Valena, thinking about something else.
No, I'm thinking now, what is viscosity like microscopically?
Right.
Is it like, it's some kind of scattering, but with when like
diffusion.
Okay, but before we had like inelastic scattering.
Correct.
And like we had two scattering integrals.
Right, but for electron,
which one of them is responsible for viscosity?
So let us look and see. So we had this separation. Oh my goodness, why stop? So we said we wrote a solution for distribution function that's essentially a thermal part that we only consider so far. And there was some correction to it, which we have neglected. Now, when we compute collision integral on the whole thing, it's a collision integral of the Fermi, let's call it Fermi-Dirac plus delta F. And if delta F is small, I can linearize and expand. And this will be only this thing because collision integral nullifies the equilibrium distribution function. Now, in a very crude way, I can say that this thing is just delta F divided by tau EE, where tau EE will be electron scattering. Time. And we know that electron scattering is in general inelastic. So let's use this as an estimate. Let us use this as an estimate. Then what we have in Boltzmann equation is dt over F PRNT plus V P times gradient R F of PRNT. And on the right-hand side, there is delta F divided by tau EE. Now, here on the left-hand side, we can use and replace this thing with the Fermi-Dirac distribution function. So we'll have d over dt f of epsilon p minus vp minus nu over t plus vp grad f epsilon p minus vp minus nu over t. All this is approximately equal to delta f over tau EE. So let me call this thing, the entire combination, let me call it Z, just denoted. And this is Fermi-Dirac, So the left-hand side of this equation is d over dz of F Fermi-Dirac of Z times dz over dt plus Vp times grad Z. And it's equal to the right-hand side of this equation, delta F tau EE. So it means that delta F is roughly equal to tau EE dz over dt plus Vp gradient R of Z d over dz F Fermi-Dirac of Z. And this is the correction that we need to take into account to all the tensors we computed before. In particular, our tensor P alpha beta will now become P alpha beta plus correction. Terms that were missed, terms that will be associated, will be coming with from delta F. And this thing is delta P alpha beta. If you remember, it was M integral D3P V alpha V beta times F of P. Now it will be delta F, the thing that we missed. And I just plug delta F into here, right? You follow? Okay, so just plug it in, and I'm getting that this is tau EE. Why it's not writing? Tau EE over tau EE over M integral D3P P alpha P beta P over M gradient R epsilon P minus V capital P minus nu divided by T, d over dz, F Fermi-Dirac of Z. And this is equal to tau EE over M squared integral d3p, p alpha, p beta, p gamma. Is it gamma? That's p gamma. dv delta gr gamma p delta times -1 over temperature d over dz fz Fermi-Dirac. And all this is equal to m tau EE divided by m cubed d3p p alpha p beta p gamma p delta dv, this is the velocity, component delta, dr, component gamma, sum over all indices that are repeating, d over d epsilon f Fermi-Dirac of epsilon. And now I need to compute all these integrals. It's roughly a few pages of calculation, but I'll skip all that. So now lots of integrals to compute. And I'm getting, okay, maybe I'll just write one intermediate step, tau EE over m squared dv delta over dr gamma, delta alpha beta, delta gamma delta, integral d3p, p alpha square, p delta square, df over d epsilon, plus, and here's the term delta alpha not equal beta, times integral d3p, d alpha gamma, d beta delta, plus d alpha delta, d beta gamma, times p alpha square, p beta square, df over d epsilon. And I'm getting that this thing will be equal to viscosity coefficient eta well, I call it R, dr alpha minus 2/3 delta alpha beta dv alpha dr alpha plus another viscosity coefficient psi delta alpha beta dv alpha over dr alpha, where this viscosity coefficient, say eta, is tau EE over m squared integral d3 pi p in the power 4 df over d epsilon. And now we can compute it explicitly and get that it is equal to tau EE p Fermi in the power 4 times density of states divided by m squared. And this is equal to LEE times V Fermi times rho. LEE is energy. So LEE is V Fermi times tau EE is inelastic mean free path. How long it takes for energy to be exchanged, and rho is density of electrons, density of fluid. Now, so there is a relation that we have established that viscosity of these fluids scales as a mean free path V Fermi and density. And now the question is, how does this thing scales with temperature? Now, so I can write it as V Fermi square times tau EE times rho. And I can ask how the viscosity of the fluid changes with temperature. And you should be able to answer this question by now. What in this equation changes with temperature?
Can you scroll up? Well, the mu, this like.
But let's look at the final result. So both parameters here are temperature dependent and both are not. Rho is temperature dependent. Sort of. So let's discuss low temperature limit. What happens when T approaches 0? What happens with these things when temperature approaches 0? So I have electronic fluid in the box. I have a big box full of electrons. And I'm setting the temperature of the fluid to 0. Fluid is made of electrons, as opposed to water molecules. So I can change temperature to 0 and still this fluid will not freeze. Right? That's the big difference between electrons and water molecules, because water molecules will freeze. Electrons will not. So what will happen to these parameters?
So I think something will happen to this inelastic scattering lengths.
So what can we say about inelastic scattering lengths for electrons as a function of temperature?
So when temperature goes to 0,
yes,
I think this should go to 0 also.
Tau E.
No? Or infinity.
So which one?
Infinity, I think.
Infinity. So how is it scales with temperature? A hint, we discussed it last time.
Don't remember. I don't remember.
That's a Fermi liquid theory scattering rate. How in Fermi liquid lifetime depends on temperature.
Okay. Well, it depends on dimension. So if we're in 3 dimensions.
In 3.
Maybe log, no?
So it will be a function of energy. How it will depend? Maybe that will be easy.
Log, no?
Tau lifetime of electron at energy epsilon. What is it?
Sorry, okay, let me guess.
It must have a dimensions of time.
Ah, yeah, okay. Okay. And when I do, so it's 1 over n 1 over energy, 1 over energy. Oh?
No, if this would be the case, that epsilon tau epsilon
Okay,
will be 1.
And energy is
That has
there
a
should be some like, okay. I mean, it's proportional to 1 over epsilon.
yes.
There is some constant proportional. Right.
Forget constants.
Okay.
So for particles,
so when I divide like 1 over tau by energy, this should go to 0. When energy go to 0,
correct.
Right? It should have this property.
Yes.
So then I guess there should be like epsilon.
Epsilon times tau of epsilon must be much larger than 1. Otherwise, there is no meaning of energy.
Much larger than 1 when epsilon goes to 0.
All right. So what can you construct such that it has dimensions of energy and goes to?
No, I would say like log.
Forget logs are not. What
Exponents? No, not exponents. So there should be some dimensionless.
Right.
Okay. So tau is 1 over epsilon times some dimensionless function of epsilon.
No, it's not 1 over epsilon.
It's not 1 over epsilon at all.
It's a different power.
It's 1 over epsilon squared.
Right.
Okay.
It's 1 over epsilon squared. And that's why tau epsilon times epsilon is epsilon Fermi over epsilon, and that diverges at small epsilon. So if you have, that's the scaling with energy. And roughly it's the same scaling with temperature. So if you say what is tau as a function of temperature, it's 1 over tau, it's t squared over epsilon Fermi. Yeah? So that's the key thing of electron scattering, because this is what allows us to treat quasi-particles at low energies as quickly interacting. So it means that here, this is the only object that diverges, all other objects remain finite. And therefore, if you look at this expression, that at low temperature, this thing scales as V Fermi square epsilon Fermi times temperature square times rho. So it essentially, in the low temperature limit, the viscosity goes to, so when temperature goes to 0, the viscosity goes this is viscosity.
It's proportional to tau, right? So to infinity.
To infinity. So system of electrons has infinite viscosity as temperature approaches 0. It is way more viscous system than honey. So that's actually a typical thing about these quantum fluids. You look at the system of quickly interacting particles. The viscosity in the system always proportional to the mean free path. Mean free path always diverges as you lower the temperature. And therefore the viscosity of the quantum fluid always diverges at low temperature. It may seem paradoxical, but that's very counterintuitive. You're not first people to be very puzzled by that. But remember that actually it's not as counterintuitive, because in order to describe something hydrodynamically, we need to look at it at scales which are much larger than mean free path. So it's true that once you look at the system beyond mean free path, it's a very viscous fluid. But the problem is that when you lower the temperature, it requires longer and longer scale to reach this hydrodynamic limit. Yeah? So it is a very viscous system at the limit, which also diverges with but the regime of hydrodynamic itself also diverges when you lower the temperature. So you will see this behavior with a very large viscosity, but only on the scales that themselves are diverging in the low temperature. Still, it's a very unexpected and puzzling a feature of quantum fluids. Okay, so I think that I delivered the main message how you go from kinetics to hydrodynamics. I'm mostly interested in electrons, so that determined my choice of looking at electrons and not in a degenerate regime rather than, I don't know, water molecules. You can, of course, repeat this analysis for temperatures which are well above chemical potential and get a classical hydrodynamics in its more conventional forms. Okay, I think I finished this. So next lecture, I'll be talking about noise in solids. Okay, I guess that's it. So let's stop sharing. By the way, I think there was no people in this, but probably someone will be listening to.
No, there's someone